Okay, well, hello and welcome to class. It's good to see you guys. Thanks for turning on your camera. And all right, we'll take a look at today's stuff. Week 3 Wednesday. All right. So we're gonna take a look at neural networks today. All right, which is quite exciting. We're gonna actually depart from the textbook. The textbook doesn't say anything about neural networks, but I don't know. Neural networks, I think, are cool, and um, and it's a good application of gradient descent. So, in homework 2, I have you guys kind of mess around with gradient descent, and neural networks is like the gradient descent is popularly used in for neural networks. So I want to kind of talk about that, and we'll approach neural networks as from an optimization perspective. But let's just spend a moment doing a quick review of gradient descent, and this is what I don't know. This is what your homework's all about. Oh, so I have posted homework 2, by the way, on CCLE, and it's I don't know. It's a little bit long. Like the document that you produce is going to be very long. Okay, there's like a whole bunch of stuff. All of the instructions are in the output file itself, so that also just makes the document really long. One suggestion is you can just try to knit the instructions files as is, and you'll get this, kind of this PDF that you can kind of read through almost as instructions as you work through creating the output. Okay, each task in of itself shouldn't be unimaginably hard. It should, and if you refer to kind of the lectures that I've given, there's a lot of the answers you can find in the lectures already, but it will force you to kind of read through the lecture kind of carefully to seek out what the tasks are asking you to do. Okay, so anyway, let's review gradient descent. And what we are trying to do is, when we do gradient descent, we've got some kind of function that takes in a vector. And in our case, we have a function of w kind of representing our vector of weights or a vector of coefficients for, linear regression, or in our case, when we do neural networks, yeah, it'll be a vector of weights or even a matrix of weights. And so we have a function that takes this input, and what we're trying to do is we're trying to find the values of w that will minimize this function. Okay, and so gradient descent is this iterative thing where, if we start at some arbitrary starting location, which we'll call w at time t equals 0, right? So w at time t equals 0, how do we select the next location, w at time t equals 1, right? So you guys remember what we do in gradient descent is we take our current location, or current value for w at time t equals 0, or w at time n, and we calculate the gradient of the function, and all we do is we take a step backwards, right? So the gradient of the function points in the direction of steepest descent, okay? And what we do is we just say, you know what, I'm going to walk in the direction opposite of going uphill, and that means I'm going to be going downhill, right? So if I say, all right, which way is uphill? We're going to say, okay, that way is uphill. I'm going to go in the exact opposite direction, and that will take us downhill. Okay, and we just kind of multiply. So nabla f here represents the gradient, represents the gradient of f at location w at time n, and we're going to take multiply that by some function constant gamma, some generally a small value, because the gradient is often a very big number, and so we're going to take our current vector w and subtract off the gradient, okay, at vector w, right? And so in order to kind of do this subtraction thing, an important thing to remember is that the gradient and the vector itself have to have the same dimensions, right? If these don't have the same dimensions, you can't add and subtract them. So if w is a 3 by 1 vector, your gradient needs to be a 3 by 1 vector. Otherwise, you can't subtract them or you can't add them because the dimensions won't line up, right? So I frequently recommend writing the dimensions underneath of these things just to kind of make sure that your operations are going to work, right? And that will give you the value of the gradient or value of the vector W at the next iteration, and you just continue from there. Okay, so far so good with everybody. Just this review of gradient descent. All right, let me go ahead and give you your first view quiz answer today. First view quiz answer today is D. D as in dog or Disneyland, D. Disneyland is reopening at the end of the month, right? I think at limited capacity. They had I think they have something called Taste of Disney already going on, which is like everything is closed, but you can just walk and look at the park empty. I don't know. Okay. All right. So we're gonna do a very short introduction to neural networks. All right, and it'll take us a couple lectures just because I'm going to be doing I don't know, a bunch of stuff talking about it. Okay. So there are a lot of really good resources on YouTube, and I highly recommend it watching these playlists. Okay. And so this one is Neural Networks Demystified. Okay. Part 4 is 8 minutes long, and it's on back propagation. If you get lost here, don't worry. I'm going to spend like an hour covering back propagation. Okay. So, so I'll explain all of this stuff in this part of the video, but I mean, maybe you follow along and it makes totally sense. Okay. And then neural networks from this channel, 3 Blue 1 Brown, which I highly recommend. You should be subscribed to this channel. I'm subscribed to both, but I highly recommend this. This playlist is also excellent. This one's maybe a little bit longer, but the visuals and the graphics for this, very impressive, and it makes very clear what's happening. So definitely check these playlists out, and shout out to both of these channels, and I recommend subscribing to them. Okay. As far as this class goes, we're going to look at the simplest of neural networks, okay? And technically, neural networks have been around for decades now, but they're like super popular these days because we finally have the computational power to do these very complex neural networks, okay? So as far as this class goes, we're going to look at like the simplest neural network, okay? And even though it's simple, it still has decent predictive power, okay? But lately, we've researchers have been making these very complicated and deep neural networks, and they've been used with great success for image applications of image recognition and kind of like real-time processing of video feeds and things like that. Okay. So, as far as this class goes, we're only going to look at the simplest kind of a neural network. You can take an entire course on neural networks. It's not even necessary. Like, there's nothing in the 102B course description that says we should cover neural networks, but I think they're kind of cool. I think it's a neat thing. I wanted to cover it, so I'm just like squeezing it into our course here. Okay, but it's not part of our textbook, not part of anything like that, right? So, first of all, what is a neural network? Okay, at the simplest sense, what a neural network is it's basically a function. Okay, it's a special kind of it's a way you design the function, but basically a function takes an input and it gives an output, okay? And a neural network does the same thing. It has an input, it does some math, and it spits out an output. And that's basically all a neural network is, okay? Now, as far as what that math is doing, it's kind of inspired by, I guess, the way the brain works, in that, your brain has a bunch of neurons that are all kind of connected to each other, and you have these these synapses, and a neuron is activated, and when it's activated, it shoots a little electrical impulse to to other neurons, and based on the impulses of that neuron, it shoots things, and somehow all of these electrical pulses happening in your brain, millions of them happening every second and stuff, is enough to give rise to thought and conscious thinking. And who knows how it works. It's quite mind-blowing that that we're able to speak and listen and see and communicate and feel, and all of that. And at its heart, it's just electrical impulses being sent around, but I don't know. Okay, so in a biological brain, a neuron is going to receive input signals, and depending on that signal, the neuron might send a pulse, an activation potential, to other neurons. And when we create kind of like this artificial version, this artificial neural network, we're going to have some nodes, and they're going to get input values, and depending on the input value and the activation function inside of the node, it might send out new values to other nodes. Okay. And so, I'm gonna follow this silly example. And this is an example taken directly from the Welch Labs video. And so, I do recommend that you watch the Welch Labs videos, as they kind of give an overview of the example that we're going to run through. Okay. And so what we're going to do is we've got an input matrix X, and we've got output values Y. Okay. And so this is, there's only 3 values in our input matrix. Okay. We've got 2 columns. Okay. And so our input matrix X has 2 variables. One represents the hours of sleep. Okay. 3 hours of sleep, 5 hours sleep, 10 hours of sleep. Okay. And then the second column is how many hours was spent studying. Okay. So 5 hours were spent studying, 1 hour was spent studying, 2 hours were spent studying. Okay. And then the third, and then the output values Y represents the exam score. So scored 75, 82, and 93. Okay. And so what we want to do is we want to be able to train the network so that, given some set of input values, we can predict the output values. All right. And so, our training data has a total of 3 rows. This is very, very little. This is not a whole lot of values to use for as far as training data. Generally, you want, thousands of input things, but you can do all kinds of stuff. Let me see. Did I? Okay. Yeah. Great. Okay. So when we create our neural network, what we're going to do is we start with an input layer, and we're going to end with an output layer, right? And so in our input matrix X, the input values, we have 2 variables, right? We got hours of sleep, hours spent studying, okay? And so we have 2 variables. Each of those will have kind of an input node. So during our input layer, we're going to have 2 nodes, one for hours of sleep and one for hours spent studying, okay? And our output node is going to be the score on the exam. So there's only just one value in the output node, or one node in the output layer, and that's the exam score. Okay. And in some cases, you want to like predict categories and stuff, and you're going to have basically an output node for each category, but we won't get into that right now. We'll just have the output layer, right? And so what a neural network will consist of is it's going to have some hidden layers, right? So you have your input, they go through a hidden layer, and then they reach the output layer, right? And so for our simple example, all we're going to do is we're going to just have one hidden layer with 3 nodes, okay? The choice of having 1 layer is arbitrary, and the choice of having 3 nodes is arbitrary, okay? I'm just choosing small numbers to kind of keep our introductory example very simple. But basically, if it works for 1 node, 3 nodes, we can generalize to 5, 100, 1,000 nodes in the hidden layer very easily. We're going to use matrix notation for all of this. And by using matrix notation, we can kind of generalize the number of nodes very easily. Okay, so and every node in each layer is connected to all the nodes in the next layer. All right, so this is what our diagram is going to look like. Okay, this is my input layer. I've got two nodes, basically one for hours of sleep, which is going to be x1, and one for hours of study, which is x2. Okay, and the inputs are n by 1. I've got 3 observations. So, 3 values for hours of sleep, 3 values for hours of study. If I had more observations, that would just grow by n. Okay. And again, arbitrarily, I chose 3 nodes in my hidden layer. We could have chosen any other number, but just to kind of keep it simple and illustrate how this works, I got 3 nodes in my hidden layer. And then I got 1 node in my output layer representing the exam score, which is going to be y bar here, or y hat. Okay. This is going to be our predicted value. Okay, so once it goes through our neural network, we're going to get predicted value y hat, and we would compare our predicted value y hat to the actual value y to kind of see how well our predictions are doing. Okay, so you might have heard about deep learning. Okay, and so in our example, we just have 1 hidden layer, but you can have a bunch of hidden layers, right? You can have 2, you can have 100 hidden layers and stuff like that. And if you have a whole bunch of hidden layers, we might call this a deep neural network because there's a whole bunch of layers. It's, the structure of the layer is very, very deep, okay? And this has been shown to be incredibly powerful. And so kind of there's this classic competition called the ImageNet competition. And it's this data set containing 14 million images, okay? And every image has, thousands of possible categorical labels, right? And these are hard, right? First of all, the images are fairly small. And then the labels could be something like, it's not just like cat and dog, but it'll be like, oh, that's a poodle or a corgi or, French bulldog or something like that, right? As far as the image set goes, only certain types of images appear and things like that. But yeah, there's thousands of possible categorical labels. And for a long time, humans would always beat the computers. But then in 2015, and I guess that's already 6 years ago, it just feels like not that long ago when this happened. I remember seeing in the news, this was a big deal, at least in the computer vision world, okay? When a convolutional neural network surpassed the human error rate for labeling images, okay? I think the human error rate, I think the humans are able to correctly identify it like 95, 96% of the time, just because there's thousands of categorical labels and it's easy to just accidentally, or not even accidentally, but like get mixed up as far as like, oh, is this is this type of dog or some other type of dog or something like that, right? And so as far as the labels go, there is, humans aren't perfect, and the convolutional neural network beat humans in 2015 for the first time, and then the performance has just kept getting better and better and better, okay? And then here's this video, and this blew my mind when I first saw it. This video is already 4 years old, or 3.5 years old now, okay? This is a convolutional neural network, I think a recurrent convolutional neural network. And basically this is, it's being applied for, trying to power self-driving cars, right? Because we want that, I think, right? And so, so this is a video feed of, somebody driving their car. It looks like in Europe, and the computer is labeling all of the objects that it sees that it believes are relevant, right? So it's labeling, okay, these things look like persons, and it's 99% confident that this is a person. This structure is a car, and it's 98% confident that this is a car or something. And this thing up here is a traffic light. And so this is just happening kind of real time. And, the video feed is just coming in as, this streaming video feed. And it is, it's labeling all of this stuff in the image as far as, what it believes to be the thing. And this is powered by a neural network. we are not going to do anything even remotely 1/10 as cool, okay? I don't know. It's kind of cool. We'll do nothing that neat though, all right? We're looking at the simplest of the neural networks, okay? And so, one thing to note though, is that neural networks are really, really, really good for predicting stuff, okay? It has very strong predictive performance, okay? As far as interpretability, neural networks are total, like you have no idea what any of the coefficients in a neural network, any of the weights that we figure out in a neural network, those are total mysteries to us, okay? Much like the human brain, like you can study neuroscience, but we have no idea what's actually happening inside the human brain, right? Like we have, a little bit of idea of like how some stuff works, but somebody says like points to a neuron here and says, okay, what's happening with this neuron? Like, or this thing does, we look at someone's brain and we say, well, what's going on inside their brain? We don't really know. And that's kind of like how neural networks are. Is we look at the neural network and we go, hey, what's happening with this node? And we go, I don't know. It's a mystery what's happening inside, what the values themselves mean. But we can say, hey, look at this. It's predicting the numbers really well, okay? So, all right, this is our simple neural network that we're looking at. 2 nodes in the input layer, 3 nodes in the hidden layer, 1 node in the output layer. Okay, and so first we're gonna just talk about how the neural network takes an input value, pushes it through the neural network, it's called forward propagation here, and it produces a predicted value, okay? And so if you look at this diagram, we have a total of 6 arrows, okay? Because this node is connected to all the nodes in the next layer. So we have 3 connections from this node to the next layer, and we have 3 connections from this node to the next layer. So we have a total of 6 connections, and each of these connections are going to have a weight, okay? Each connection has a weight, and we're going to say, this node plays, is weighed heavily here, and maybe this node is weighed lightly here, and who knows, okay? But we're going to have 6 connections from the input layer to the hidden layer. And if we look at the hidden layer to the output layer, there's 3 connections, okay? So we have 3 connections from the hidden layer to the output layer. And so all of those connections get associated with a weight, and that weight is going to be kind of how, quote unquote, important that connection is. But again, we don't really know exactly what is happening. But what we're going to do when we talk about training the model or training your neural network, right? I'm training my network. That sounds like a thing that I don't know, people talk about. It really just comes down to what are the weights that I should use for these connections. Okay, so if I label all of these things, this is how we label them. Okay, this connection is going to be labeled W11 because it's going from the first node to the first node. This connection is labeled W12 because it's going from the first node to the second node. And this red one in red is W13 because it goes from the first node to the third node. Okay, this connection here, this one is called W21 because it goes from the second node to the first node. W22 goes from the second node to the second node. W23 goes from the second node to the third node. Okay, these all have a superscript of a 1 to indicate that this is associated with the first set of weights. Okay, the first set of weights. So we got 6 weights in our kind of first set of weights. Over here, these all have a superscript of 2 because they are associated with our second set of weights. In our second set of weights, we go from the first node to the first node, so that's W11. There's only 1 node here, okay? From the second node to the first node, W21. From the third node to the first node, W31. And to indicate that these are part of our second set of weights, they all have superscript 2. To indicate these are first set of weights, superscript 1, okay? And then here, these nodes, we call them Z, and this has a superscript 2 to kind of indicate they're in our second layer, Z superscript 3 to indicate that it's in our kind of our third layer of our output layer. Is that all right as far as the notation for labeling all of these connections? Okay, great. Let me go ahead and give you your second view quiz answer. Second view quiz answer is C. C as in California. C. C as in cat or connection or California. Okay. That's the second U-quiz answer for today. All right, so we're going to gather the weights into kind of weight matrices. So we got big W1. Okay, this is our first weight matrix, and this is all of the weights going from our first layer to our first set of weights. Okay, first layer to the second layer. Okay, and so we're going to arrange them, and we've got W11, W12, W13. This is going from the first node to the second layer, node 1, 2, and 3. And this second row is for the second node going to this second layer, W21, W22, and W23. Okay, so we have 2 rows, 1 for each node in layer 1, and 3 columns, 1 for each node in layer 2. Right, so this is a 2 by 3 matrix. Whereas W2, W superscript 2 is our second weight matrix, and that goes from the second layer, or the hidden layer, to the output layer. And it's going to have 3 rows because there are 3 nodes here, and it's got 1 column because there's only 1 node here, right? And so those 3 weights, W11, W21, and W31, all with a superscript 2, are going to get arranged in this 3 by 1 matrix, right? And I've tried to coordinate the coloring of these, I don't know, coefficients or weights with the coloring of the arrows and the diagram here, hoping that it helps and makes sense. Okay, so to get the values, right? So we're going to take the input matrix X and multiply it by our first weight matrix, right? So the input matrix X has n rows and 2 columns. We have n observations and 2 columns, and we're going to multiply by our first weight matrix, which is 2 by 3, and that's going to result in our Z matrix, which will have n rows, 1 for each observation, and 3 columns, 1 for each node in the second layer, the hidden layer. Okay, so when you do this, you're going to, all of these get multiplied like this, right? So we're going to have n rows, and we have 3 columns. All right, is that okay? So I'm just doing matrix multiplication, and I'm hoping these matrix operations make sense here. And hopefully the colors help as far as what's happening. Okay. And then what we do is we apply what's called a activation function to the resulting matrix Z. Okay. So once the values get to that second layer, now that we have n observations and 3 nodes, we have an n by 3 matrix, we're going to apply an activation function to all of the elements in Z, all right? And what the activation function does is it kind of just introduces a little bit of nonlinearity. You could just leave it, okay? But then everything is going to just be a linear combination. And so the activation function brings in a little bit of nonlinearity. And so the dimensions of Z will remain the same, okay? Z is n by 3 matrix. If I apply the function to each element, the result will still be n by 3. And we're going to just call this A to kind of indicate it as the activated values, the values after I apply the activation function, right? And so as far as the activation function, what we will do is we will use the sigmoid activation function. This is basically a logistic function, okay? And it looks like this, okay? This has fallen out of favor these days, but what basically does is it takes all of your values. So your values on the domain is negative infinity to positive infinity, and what it basically does is it squishes all of them onto the range 0 to 1, right? So you get values bigger than 8, you get something very close to 1. Negative 8, you got something very close to 0. And around 0, you have, at 0 you have 0.5, and between here and here you've got some kind of value here. Okay, so as of late, the sigmoid activation function has fallen out of favor. Okay, a lot of neural networks today use what's called the rectified linear unit, or the ReLU activation function. Other choices are the hyperbolic tangent, or what's called a leaky ReLU, and you can read an article on Wikipedia with about all of these. So this is the logistic or the sigmoid activation function. And then here's a whole bunch of other choices, right? So you can leave it as the identity, but you also have all of these different options for activation functions. And we'll just stick with the sigmoid activation function because, well, it was popular historically, right? Even though it's not popular today, historically it was popular. It's also kind of used in these, in both of the video series, the one from 3 Blue 1 Brown and Welch Labs. And so we'll kind of stick with that. But that's what we'll have, okay? So again, we've got our inputs X, we're gonna multiply it by our weight matrix W, and we get Z. We apply the activation function to Z, and now we need to go from the values here, after we've activated them, A, and we're gonna get to this. So what we're gonna do is we're gonna take the values and we're gonna multiply it by our second weight matrix, okay? So we have the activation function value, activated values, okay, which are in matrix A2, okay, and that again is an n by 3 matrix. We have n rows, 3 columns, 1 column for each node in the hidden layer, and we're going to multiply it by the second weight matrix. The second weight matrix is 3 by 1, right? We've got 3 weights, and they're all going to 1 node in the output layer, okay? And so when you multiply, so this looks a bit scary, but this is just an n by 1 column matrix, okay? When I multiply the n by 3 by a 3 by 1, the result is going to be n by 1, right? Because the way matrix multiplication works is, you know, this gets multiplied and I add on this and I add on this, okay? So what's happening is the values that come into here is basically this times this plus this value times this plus this times this, right? These 3 arrows come in and they're all being added together into just one value, okay? So each observation will just result in one value here, which is what we want. We only want one, as far as a prediction goes, we only want one predicted value for each observation, okay? And so this is the resulting value that we get, okay? It's the combination of the activated value for, you know, so we're gonna have n observations here. So, you know, our first observation, first node times weight 1, 1, first observation times at the second node times weight 2, 1, first observation at the third node times weight 3, 1, okay? All the way down to the nth observation at the first node times weight 1, 1, nth observation at the second node times weight 2, 1, nth observation at the third node times weight 3, 1, okay? Added that, okay? And then lastly, we apply the activation function one more time to introduce again some nonlinearity or, you know, some adjustments here. And so we're going to get Z3. And if I apply the function to Z3, I'm going to get Y hat. This is our predicted value. So the value predicted by the neural network is going to be this. And that's not going to change the shape. This will remain n by 1. Okay. So to summarize all of the matrix operations, we take our input, we take X, and we multiply by our first weight matrix W. That gives us Z, Z2. We apply the activation function to Z, the Z values in our second layer. That gives us our activated values in the second layer. We take the activated values in our second layer and we multiply by the second weight matrix, W2. And that's going to give us our Z values in the third layer. And we're going to take the values in the third layer. We're going to apply an activation function there. And that's going to give us our predicted values Y hat, okay? We can kind of combine all of this into one line and we can say Y hat is the result of X times W inside a function, multiply that result times W2 and put that inside a function, right? So it's going to be F of X W1 times W2. Is this all right? So I'll just say this is how we go from the input values to the predicted values. The Welch Labs video does not include what's known as a bias term, okay? And bias terms are frequently used in neural networks, okay? And basically, all they do is they just add a constant. They just add a constant at each node before you apply the activation function, right? So here, all I'm gonna do is I'm gonna do, you know, W the same operations, but once I get here, I'm going to add a constant. Okay. I'm going to add a constant for this node, a different constant for this node, and a different constant for this node. Okay. So I got B1, B2, and B3. And this is kind of our first, they have a superscript of 1 to indicate that these are the constants for the first set of biases. Okay. And then here we have, there's only one node here. So this is just B1 and it has a superscript 2 because it's the bias for the second set of biases, but it's just one bias term here. Okay. Now it's important to note that the same bias is going to get added to all observations. Okay. So all of your n observations that end up at this node, or the values that end up at this node, will get the same constant here. The same bias value gets added here. For the second node, the same bias value gets added. For the third node, the same bias value gets added. Okay. The three nodes have different bias values, but those same bias values get added across all observations. Okay. So as far as this goes, okay, the matrix of biases is a 3x1 matrix. Okay. So there's one bias term for each node. So our matrix of biases is going to be 3x1. Okay. But I won't be able to add 3x1 to the result of xw, right? So if I take x and I multiply by w1, the first weight matrix, x is an n/2 matrix, right? I've got n observations in 2 columns, and w1, our first weight matrix, is 2x3. So this result is going to be n/3. Okay, and this is 3x1. So I can't just take 3x1 and add it to this n/3 thing. Okay, and so in order to kind of get it to work, well, we have to think about what does I go back here and we think about what does this n/3 represent when I take x and I do w, right? This is the value at the first node. This is the value at the second node. This is the value at the third node, right? So we got the value at the first node, value at the second node, value at the third node. Okay. And so what I need to do is I need to add a B1 here, and I need to add the same B1 to this value, and I need to add the same B1 to this value down here. I'm going to add a B2 to this one. This is at the second node. I'm going to add the same B2 to this value at the second node. I'm going to add the same B2 to this second node here. I'm going to add the same value B3, or a new value B3 to this node. B3 gets added to this node, and B3 gets added to this node. Okay. So in order to get the dimensions to line up, we have to multiply our B's by a matrix of just ones. Okay. Just a matrix, or I'm sorry, a column of ones, an n/1 column matrix of ones. We're going to multiply that by B1 transpose, and this will end up being an n/3 matrix. Okay. And so this is what it looks like. Okay. So when I do x times w, this is going to multiply out to be n/3. And this j, which is n/1 multiplied, and I apologize, I don't know why, but I can only get this light neon green that's hard on the eyes. I got to look up a better color here. All right. So I apologize for the hard on the eyes green here. This is going to get multiplied by j times B1 transpose will look like this. And this will become an n/3 matrix. And so I can take this n/3, the result of this is n/3, and the result of this is n/3. And then I can add them together, and the result is also going to be n/3. Right? Is that okay? Is that clear what's happening as far as the matrix multiplication goes? So that's an n/3 and an n/3. We add them together, and the result is going to be n/3 as well. Okay. Same kind of thing. We do the activation function there. Going back over here, we apply the activation function. We get a, which is going to be n/3. And now we multiply it by w2, which is 3/1. And now I have to add on B2, okay? And so A is n/3, W is 3/1. So this is going to result in a 3/1 matrix. I'm sorry, an n/1 matrix. This is an n/1 column matrix. And I do the same thing. I'm going to have J, which is just a column of ones. and you're going to multiply it by B2. It's technically B2 transpose, but I mean, this is just a constant. So, you know, a scalar value transpose is still the exact same thing, but this will become an n by 1 column as well, right? And so we take this and we multiply those things together. And now we have Z3, which is also, we add them together. And now we have Z3, which is n by 1. Okay. And so the key here is to remember that the same value B1 is getting added across all n observations here. Okay. And so as far as the summary operation here, as far as y hat goes, okay, we have xw1, x times w1 plus j times b1 transpose. That's going to result in z2, which is n by 3. We apply the activation function f to z2, which is n by 3. That gives us a2, which is n by 3. We take a2 and multiply that by w2. So that's an n by 3 by 3 by 1, which this is going to be n by 1. And we add that to j times b2 transpose, which, I mean, b2 is just a 1 by 1. So this multiplies out to be an n by 1. And so this combines to be z3, which is an n by 1 matrix. And then we apply the activation function there, and that gives us our predicted values y hat, which is n by 1, which is exactly what we want. We only want one predicted value, at least in our case, for the n observations. So we would have n y hat values, and that's what we have. Okay, and so in summary, y hat, in this case, if you have biased terms, is going to be f of xw1 plus jb1 transpose. That result times W2 plus JB2 transpose. There. Okay, why do we need the bias terms? Okay, you don't, I mean, it's like having an intercept. It's just a little, it's an extra parameter that sometimes can add the little extra flexibility that you might need when in trying to fit your model, right? So, you know, can you fit a line without using an intercept? In some cases, you can do a good one, and in some cases, you need that. Or I mean, having that intercept is helpful. And just like that, having a bias term can sometimes be the adjustment that you need. And so it's just an extra term. We're just basically adding a constant. And so, you know, as far as what the logistic function is doing here, it's just going to basically slide the logistic function either up or down the x-axis there. Okay, let me give you your last view quiz answer for today. Last view quiz answer is A. A as in apple. A as in apple is your last view quiz answer for today. All right. Okay, and so what we're going to do next is we want to measure how good are the predictions that we're getting, right? So all we've done so far is we're saying we've got input values, we're going to put them into our network. Our network, you know, does this multiplication stuff, adds bias terms and stuff, and then it outputs a predicted value y hat, okay? And what we want to do is we want to get the y hats to be as close as possible to the actual values y, all right? I mean, this is the same goal as linear regression. You want your predicted values y hat to be as close as possible to the actual values y, right? And so you're trying to just shrink that distance. And so all we're going to do is we're going to just take our residuals in vector form, or I mean, we're just going to do the sum of squared error, right? We're going to take the difference between the actual value y minus the predicted value y hat. We're going to square those and add them up. In matrix form, that's y minus y hat transpose times y minus y hat, right? And so this is basically a way of doing sum of squared error, right? And if you want mean squared error, you do this times 1 over n to kind of get it to be the mean squared error, okay? Now, what we have to keep in mind, and this is what's going to get hard in the next part, is that y hat, this consists of this kind of wonky function here, right? So this is, if we have no bias terms, it's this. And if we do have bias terms, it's this, okay? It's kind of a mess, right? And so what we're going to do starting on Friday is we are going to we want to optimize the loss function. And the way we're going to optimize the loss function is we're going to find the gradient of the loss function with respect to W1, and then also later on find the gradient of the loss function with respect to W2. And we're going to apply gradient descent, and we're going to find the value of W1 that minimizes the loss function. We're going to do gradient descent. We're going to find the value of W2 that minimizes the loss function. Okay. And so hopefully we can find the values of W1 and W2 that minimize the loss function, in that when we talk about minimizing the loss function, the difference between the actual values Y and the predicted values Y hat will be as small as possible. Okay. Now, taking the derivative of this, so actually what I'm going to do in lectures, I'm going to take the derivative using Y hat without bias terms. It's still a bit of a mess. We'll do that. And then in your homework, you'll do it with the bias terms, the future homework assignment. Okay. All right. So that's what we have to look forward to on Friday and also part of next week. And so we'll do that. Oh, on Friday, I should also talk about your upcoming midterm exam. So we'll do that as well. Okay. All right. So we'll end here for today. Have a good night, and we will see you guys on Friday.